we're going to go through some how to solve various related rate problems. Now, related rate problems are a very common application in calculus. The thing that makes related rate problems all relatable is that we are differentiating everything. We're trying to find rates with respect to t. Okay, so everything when we're taking the derivative, we're taking it with respect to t, whatever equation we have. Now, there's a little bit of process on when we find different equations, and that's the hardest part when finding related rate problems. So without further ado, let's go through and see if we can figure this one out. A very common problem is talking about conical tanks. Conical tanks. You know what conical tanks are? Conical tanks are cones. So what do they have in this problem is we have a conical tank, vertex down, so we have a cone, and I like to draw a picture, so whenever I do this, I always draw a picture when I do that. I want to encourage you to do the same. So conical tank, cone tank, vertex is down, is 10 feet across. So we're going to have a conical tank which is 10 feet across. All right, top and 12 feet deep. So from here is 12 feet deep, like so. All right. The water flows in the tank at a rate of 10 feet cubed per minute. So water is being flowing in the tank. So this is blue. Water is being flowing into this tank at a rate. So this is a rate. Now, when we talk about rates, we are going to talk about d over dt. All right. So something changes over time. So water flows in the tank at 10 feet cubed per minute. So 10 feet cubed per minute. Since it's feet cubed per minute, we know this is going to be a volume. All right. So this is referring to the volume, all right, of water being flowing in. All right. Volume of water. Okay. Now, find the rate. Okay, so we're going to find the rate. Find the rate of change of the depth. The depth. Well, the depth we're talking about is the height. So we're looking for another rate. So that would be d over dt, and that's going to be the height. So we're going to find the rate of the height. All right, and we'll say this is h. All right, dh dt. That's what we're trying to find when the water is 8 feet deep. So, okay, so we'll actually erase that right there. When the h, the height of the water, is 8 feet deep. Okay. So here's our information. Knowing this, what we're going to do now is we're going to, once we have our information written out, we're now going to figure out an equation. Usually what I do to figure out the equation is we look at what we're given. And usually this is one of the key ones. We have volume, okay? Volume of a cone. So that is going to be our standard equation. We're going to talk about volume of a cone. If you don't know what the volume of a cone is, basic equation is 1/3 pi r squared times h. Pi r squared times h. All right, now, once we have the volume of the cone, we are looking for dh dt. Now, what we can do is normally we would take, once we find our equation, we would take the derivative of that. However, whenever I do this first step, I always go through and mentally think about, okay, what information do we have? We have, when I take the derivative, we do have the volume, how it changes, given by that. 1/3 pi, that's a constant, so we don't have to worry about this stuff. R is the rate of the radius, okay, the rate of the radius. Well, how R changes. Well, we don't know how R changes. Okay, so this is an unknown. And h, we given h, and we have to find dh dt, so this is another one. So R is an unknown, a variable that does change, but we don't know much about. When this occurs, and this is very common for all conical problems, is what we're going to do is we're going to eliminate this R by finding another equation. And what we're going to use is something that's very, very key, is we're going to use similar triangles. And you saw me draw up here. All right, what we have, I'm going to do another color. What we have is this, and I create one triangle here, and this is the depth of the water. Wrote it in red, it's blood. No, just kidding. All right, what we have right here, we have the depth of the water. What we create then is we have this perpendicular, all right, perpendicular line, and we create two similar triangles. All right, using angle, we can see that we have this. Now, what we're going to use for these similar triangles is we're going to take the big triangle, and you realize that we actually have the dimensions of that because these dimensions don't change. The total length of the base of the cone is 10, so that means the radius is 5 feet. So 5, which is the radius, is to the height, the actual height of the cone is 12 feet, and that is to the height of that right there. Now, notice that this R of water, all right, the radius of water, does change as time goes on, because the depth will keep on increasing as more and more water is being flushed into this cone. Also, the H also changes because the depth of this is changing. We're trying to figure out what is the rate of the depth and how is that changing when the height is at 8 feet. So what we have right here is a proportion which we created from similar triangles from this cone. And that always will occur. What we're going to use with this is that we're going to actually solve for R, and this will be 5/12 times H equals R. And we can take that now and substitute it into our original equation. So we have V equals, let's go pi over 3. We're going to have 5/12 H squared times H. What we're going to have now is it's going to turn into 25 pi. We have 144 because it's going to be 12 squared. And just so you know, I got the 25 from taking 5 squared. 144 times 3. 144. And then we're going to have H squared times H. That is our volume. All right, and that's going to be H cubed. All right, so we have H cubed times 25 pi over 3 times 144. Now, I'm just going to keep it like that because I think good things are going to happen to those that weight. And what we have is our equation. All right, and remember this is multiplied. From here now, we're going to take this, and now that we eliminate all this stuff, we're going to now differentiate it with respect to t. So derivative of v with respect to t is dv dt. We have 25 pi 3 times 144, which is our 12 squared, which we got right there. All right, above. And then we have the derivative of h cubed is going to be 3h squared dh dt. From here, what we're going to do is we're going to solve now this problem. We're going to take all our values and substitute them in. Well, we know that the volume, dv dt, is 10. We're going to put 10 in for dv dt. So now we're going to solve it. We realize that these will cancel out. That's why I didn't multiply them together. I kind of foreshadowed that. All right, we have over 144. We have our h. H is 8 at this moment in time. So we're going to have 8 squared, which is 64. And we have our dh dt. From here, we can solve for dh dt. We'll have 10, all right, times 144 over 25 times 64 pi. And that equals dh dt. If you want to take out your calculator, you could do that and find out what that decimal is. And we can do is we have 10 times 144 divided by 25, and I'm just so you know what I'm doing right now. I'm punching this in the calculator that I have in my hands. 64 pi. Make sure you put parentheses in the bottom, in the denominator. And we have, I got 0.2865, and that is going to be in feet per minute. Feet per minute. And that is how fast the water level is changing in feet per minute, okay, when it is 8 feet deep. All right, so that's what we have. This is a very standard equation, all right, a very standard, not equation, but a very standard application problem with related rates. I'll have some more, but I hope this helps you out in solving some other problems.